Well, okay, I think we can continue. The next talk this morning is by Kendric Schefers, and he's going to talk us about microlocal homology and the shifted cotangent bundle.
Hi, so I'd like to thank Yvonne and the other organizers for the invitation to speak. Okay, so I'm going to first tell you about the microlocal homology, what it's supposed to do, and then connect it to -1 shifted symplectic geometry. Yeah, I guess the first section, just title microlocal homology. That's not how you spell microlocal. Okay, and so to motivate the definition that I'll eventually give, I'm going to start with the following observation. So recall that on a smooth oriented manifold, we have Poincare duality. And so what Poincare duality does is put homology and cohomology in bijection with each other. But if our manifold is non-compact, we have to take either cohomology to be compactly supported or homology to be Borel-Moore. So here we go. Okay, but if rather than a smooth manifold, we have something singular, Poincare duality fails. And so in fact, Borel-Moore homology is larger than cohomology. That is to say, cochains can be thought of as chains, but not the other way around. And on a smooth manifold, every chain has a cochain representative. So I don't mean, okay, you can make that rigorous, but at the moment, I don't mean anything too rigorous by that statement. That's just intuition. So cohomology. Okay, and here's an example that honestly I just ripped off of Wikipedia. So this is a habit I picked up from my advisor. There has to be at least one Wikipedia reference every talk. No. Okay, so what I've drawn here is sort of a, okay, well let's try to make it a bit more symmetric. Okay. So what I've drawn here is the doubled cone. So this is a surface. It has a singularity right here. But nonetheless, this is contractible. So as a contractible space, its homology is 0 in degrees that are not 0. And it's a copy of Z if I equals 0. On the other hand, Borel-Moore homology has non-zero groups in degrees I equals 2, 1, and 0 everywhere else. So okay, so this example makes plausible what I was saying. Oh, this is Z squared, so yeah, Z directs and Z. Okay, great. Okay, so this idea that when X is singular, homology and cohomology diverge, it leads to this idea that this divergence can be seen as a measure of how singular X is. Okay, and so the microlocal homology, whose definition I'm about to tell you, is an attempt to go from this idea to rigorous mathematics. So to actually make such a measure. So maybe write this idea, rigorous. Okay, so right, so we actually had a talk already about microlocal things. The microlocal here refers to microlocal sheaf theory, rather than, okay, I guess there's always connections between various things, but rather than semi-classical analysis and things of that nature. Okay. Okay. Okay, so how am I going to define the microlocal homology? Well, I'll give you the data right now. First thing I'll do is restrict attention to singular spaces that arise as zero fibers of maps. So first thing I want to do is look at okay, so the input for this construction is going to be a map F from what I'll say, map F from X to V of C schemes. So schemes over complex numbers. X here is going to be smooth. I want to take X to be a smooth complex variety. And this is a finite dimensional vector space viewed as a scheme. Okay, and so my board work should use some help here. Okay, so out of the state of a map, I'll extract the following. I want you to consider the sheaf given by the microlocalization along 0 inside of V of the push forward of the constant sheaf along F. Okay, I don't expect you to know these words. Okay, so C sub X denotes the constant sheaf with stock C on X. This F sub, what should I say, asterisk, star, okay. This denotes the sheaf push forward. And this thing is the Kashiwara-Shapira microlocalization along this submanifold 0 inside of V. Okay, right. I feel like whenever I mention names, I always get accosted by a lot of people angry about attribution and such. So I'm saying Kashiwara-Shapira because this is the standard textbook for the subject, and I want to distinguish it. Yeah. It says Shapira. Yeah. Okay. Right. Okay. So for those in the know, this this tells you what this functor means. For those not in the know, I'll try to give sort of a brief caricature of what the microlocalization does. Okay. But first, I want to step back. I want to think about a sheaf as in the following way. So you can think about sheaves as, I want to say, singular generalizations of vector bundles in which the local constancy condition is relaxed and you don't necessarily need to have, So the dimensions of the fibers of your vector bundle can jump, lots of different things can happen. And so this jumping can be seen as a sort of singularity for your vector bundle. And I want to say the microlocalization, so let me per se. So I want to say this microlocalization can be seen as a measure of how much your sheaf jumps at each point and at each codirection in, well, it will turn out to be the co-normal bundle to a given submanifold, but in your cotangent bundle. So let me say microlocalization. Okay, so y and x here don't necessarily have the meaning that they did before. Here, y is a submanifold of a smooth manifold x. Oh, and when I perform this microlocalization, I'm viewing V not as a scheme, but as a submanifold. So let me be clear about that. Okay, so the microlocalization along y inside of x is a functor that takes sheaves on x to sheaves on the co-normal bundle to y inside of x. Okay, I'm being purposefully vague about what kind of sheaves I'm considering. There's only 25 minutes. Okay, so like I said, what does this functor do? It takes a sheaf, sends it to some sheaf on the co-normal bundle, and you should think of the sheaf. Okay, well, the support of the sheaf will have something to do with the singular support of your original sheaf. The singular support of your original sheaf is a measure of this singularity that I told you about, like how much your sheaf jumps at each point. But if you sample the sheaf, like look at its stalk at each point, this tells you how much your sheaf jumps at each point and in each codirection that you pick. Okay. So you can think of this thing as sort of recording the quote unquote dynamical behavior of your sheaf in phase space. And the philosophy of microlocal sheaf theory is that it takes sheaves and embeds them into symplectic geometry. So you can see we're starting to get into the realm of symplectic things already. Okay, great. So, okay, so why did I define this thing? Well, the upshot is that sections of the sheaf, so I want to say global sections of mu 0 f star cx I should have. Oh. So this gamma denotes sections, global sections. So sections of this is actually Borel-Moore homology of the zero fiber of F. And sections of the sheaf supported at 0. So note we're microlocalizing along 0 inside of V, so I get something on the cotangent space at 0 in V. So sections of this sheaf supported at 0 this is isomorphic to cohomology of the zero fiber. So I have an object whose global sections give Borel-Moore homology of the zero fiber, and whose sections supported on 0 give the cohomology. I mentioned before that Borel-Moore homology is bigger than cohomology. You can imagine what happens if I take this sheaf and look at sections supported on various conic subsets of the cotangent space, rather than just the extremes, the full cotangent space or 0. And you should get a theory, like a family of chain theories that interpolate between cohomology and Borel-Moore homology. Okay, so this, yes.
Can you get the second homology this way?
It's a very similar idea, but no. Well, okay. I don't know, but I don't think so. Like you're restricting your attention to certain chains in sort of like philosophically it's similar to intersection cohomology, but you're considering sort of a different selection method for which chains you're considering, and I don't think they correspond. Yeah.
And sorry, there's a question on Zoom. Is the sheaf M0 F* CX a sheaf on cotangent fiber of V at 0?
Yes. Yes. Okay, so I can finally tell you the definition of microlocal homology. And so, sorry to say, I did not come up with this definition, but I will refine it in this talk. So this is a definition that was actually, so this was sort of suggested by Nadler in a grad course that he gave at Berkeley like 8 years ago or something. As far as I know, the only place where you find this is now my recent paper, but before then it was notes by Chao-Chu Yuan, who took notes. So anyway, very auspicious beginnings for this definition. Okay, so here's the definition. Right, and as you might expect, there's not a single microlocal homology, but rather a family. As follows. Okay. Okay, so this thing is called the microlocal homology with support lambda. So given a closed conic subset of V dual here, I'm identifying with the cotangent space as 0 inside of V. I look at sections. This is called the microlocal homology with support lambda. And if you'd like, you can think of what to say. You can think of the smallest such lambda that a given chain will lie in as a kind of singular support for that chain. So this lambda is supposed to be the directions obstructing a chain from being representable by a cochain. Okay. So this definition is unsatisfying because I've just told this nice story about how this is supposed to be interpolate between Borel-Moore homology and singular cohomology. And these two things are intrinsic to the 0 fiber. But here I have this auxiliary data that I've used to define this, namely a map exhibiting Z as a 0 fiber. You know, I'd like to take a singular space and just get something that interpolates between Borel-Moore and singular cohomology that has nothing to do with this extra data. And so this is where -1 shifted geometry comes in. But let me first refine this definition. Okay, so the solution. Okay, so the solution to this problem turns out to be to refine. Yeah, there should be a. This is of F. Okay. Okay, so the answer to this problem will be to where am I? Oh, is to refine this microlocal homology to a sheaf on the conormal bundle to the derived 0 fiber which I will call Z of F. Okay, what do I mean by derived 0 fiber? So there was a little sleight of hand that went on earlier. I started off by talking about manifolds, and suddenly I introduced schemes. You know, it's true that, given like a complex variety, it has some associated complex analytic space, and this is where the sheaf theory is happening. But I want to say, once you introduce the scheme structure, once you introduce nilpotence into your life, why not go the full Monty and introduce higher nilpotence? Why not work in the realm of derived algebraic geometry? So if you don't know about derived algebraic geometry, that's sort of like one sentence description of it, I guess I could give is, we're all used to resolving modules or something like that by chain complexes. Derived algebraic geometry tries to resolve bad spaces by good spaces. So it's sort of I don't want to say it's a nonlinear version of homological algebra in the setting of algebraic geometry, but you should think of it as something of this nature. It's correcting some badness by resolving by good things. Okay, so right, okay. Okay, so right, so how do I do such a thing? I'll tell you quickly. So here's what I mean by solution, i.e. So the embedding of z of f into x, this is now a derived scheme. This is still a smooth scheme. This is a map of derived schemes. Classical algebraic geometry embeds in derived algebraic geometry, so there's nothing wrong with thinking in this way. Okay, so this is something called quasi-smooth. Quasi-smooth is the derived analog of locally complete intersection. So you should think of quasi-smooth as the right notion of LCI in this setting. Right, LCI. So many periods. Okay, so this is just a fact. Because this is a quasi-smooth closed immersion, this has a well-defined cotangent bundle. Or sorry, I should say conormal bundle. So this conormal bundle, okay, I'll tell you the normal bundle. It's going to be the total space of the one-shifted relative cotangent complex. This turns out to be in this setting where the zero fiber is given by a single map. This turns out to be the trivial bundle, z times b. And so you can see here, by going derivedly, I actually bake in the base of my map into this embedding. So we're getting a little bit closer to our goal by going derivedly. But now I want to say, so recent-ish developments in derived algebraic geometry let you take a deformation to the normal bundle for this normal bundle. So why is this relevant? Well, I didn't say so before, but the microlocalization is defined using a deformation to the normal bundle of your submanifold inside of your ambient manifold. So deformation to normal bundle, you can think of it as a one-parameter family whose zero fiber is the normal bundle, whose generic fiber is isomorphic to your ambient manifold. And you can take your sheaf, pull back to this space, and then perform something called nearby cycles. Anyway, not so relevant. The point is just we have a derived version of this deformation to the normal bundle. And we can imitate the definition of microlocalization in this setting to get what I call the quasi-smooth microlocalization. So, yeah. So say have derived deformation. So you can imitate Okay, so this is my construction. Me too. Okay, so last thing I'll say. Inside of this derived conormal bundle, there sits a copy of the -1 shifted cotangent bundle of Z sub f. So, oh, can I go this way? Okay. This is -1 shifted symplectic. It's canonically oriented. And there's a very famous sheaf that lives on canonical, oriented -1 shifted symplectic schemes that categorifies Donaldson-Thomas invariants. You might ask, is the push forward of that sheaf equivalent to the microlocalization of the constant sheaf? The answer is yes. And so, okay, this is the very last thing I'll write. And so I guess you could, this is the main result, all this. So the main result is given any closed immersion, I should say closed quasi-smooth immersion, C into X into smooth X. So not necessarily the one that comes from its initial definition as a zero fiber. There exists an equivalence between this special sheaf that I told you about and the microlocalization of the constant sheaf. Anyway, okay, punchline. This thing is intrinsic to Z of F. This thing is not. So showing that these are equivalent solves our problem. Shows that this derived microlocalization actually, although you initially defined it using an embedding of Z into X, it turns out to be intrinsic to Z of F. Okay, that's where I'll stop.
Thank you, Kendrick. Any question over there?
Thank you. So it's rather a remark, not a question. So you speak about Borel-Moore homology, which is roughly meant to be generalization of homology of infinite chains from the case when you have triangulation. But there is an argument which I cannot reproduce, but which is known. There's a book by Massey, which basically says that this is not a correct way of generalization. So there is a proper homology theory should be done differently, and he explains how it is done using Alexander Spanier cochains. And this, well, how to say, heals some deficiencies of Borel-Moore homology. Maybe it makes sense for you to have a look, and we'll simply compare. It is also in the language of sheaves, and so maybe it makes sense to compare with the exposition there. So Massey, homology theory. So it's a book, rather old book. So, but
okay, I haven't heard of that, so thanks for telling me.
Yeah.
Well, we are short of time, so we will leave further questions to the coffee break, and thank Kendrick again.